Hey everybody, how's it going today? This is going to be our fourth video in our series of videos that focus on the relationship between center of gravity of the load and rigging. Now, this video may also be uploaded to the Load Chart Lab channel. If you see this on the Load Chart Lab channel, it's a standalone video. There aren't any other videos on that channel that go along with it, but if you want to go to the Safety Pro Calculations channel, you can look at the other three videos in the series. Also, if you hear a humming noise in the background, it's summer in Oklahoma and I needed to turn a fan on, so you might hear that fan in the background. My speaker's really sensitive. I did set the air conditioner so the central air wouldn't come on. That really is noticeable, but hopefully this fan is not too much of a distraction if you can hear it in the background. In this video specifically, we're going to look at the relationship between center of gravity and sling loading. The position of the center of gravity relative to the position of the pick points affects the loading on the sling. We're going to talk about that issue first, and then we're going to talk about how we can determine the pick points on our loads. We want to determine pick points so that we don't overload our rigging, or if we're using multiple cranes, we want to use pick points to ensure that we're not overloading the cranes. And more on that as we get into that particular issue. Let's go ahead and take a look at a situation that riggers, crane operators, construction crews, and also in general industry you might run into occasionally. You see a load with an off-center center of gravity, an odd-shaped load with a center of gravity that's not right in the middle. To make sure that we're not overloading our rigging, we need to determine the amount of the load being carried by each of the two slings. Again, we have our odd-shaped load. We have sling 1 carrying part of the load, sling 2 carrying part of the load. We have our pick points, and we have center of gravity is marked, and we have the weight of the load. Then we have the distance between the center of gravity and the pick point, and each pick point. But more on that as we go along. But what is the sling loading? How much of the 26,500 pounds is being carried by sling 1? How much of it is being carried by sling 2? Well, you're probably already guessing that sling 2 is going to be carrying more of the load because the center of gravity is closer to sling 2. And that is correct. Sling 2 will be carrying more of the load, quite a bit more of the load than sling 1. But we want to know exactly how much each sling is carrying. And that's what I want to show you, the method, the formulas that we can use to do this calculation. Again, the load on each sling is a function of the load weight, center of gravity location, and pick point location. The distance between the center of gravity and the pick point is our major determinant. We use the distance from the pick point to the center of gravity and the total distance between pick points to find percentage of the total load carried by a particular sling or by a particular pick point. Our total distance in this example is 12 feet. The distance between sling 1 or pick point 1 and the center of gravity is 9 feet. Pick point 2 and the center of gravity is 3 feet. Those are the numbers that we're going to be using. But one thing interesting that might be puzzling, and don't puzzle over it, just do it this way. We don't need to puzzle over the whys and the what fors and the hows of this, but we just need to do it this way. And it's going to be illustrated in the formula. But we use distance 2 or 3 feet to find the loading on sling 1. That's what these arrows represent. We use distance 2, in this case 3 feet, to find the loading on sling 1. And we use distance 1, 9 feet, to find the loading on sling 2. Again, don't worry about the whys. Again, this is an established method used by riggers for years. Just follow this method and you'll always be in good shape. And what we're going to be doing is dividing the distance from pick point to center of gravity by the total distance. This is going to give us a sling loading factor, or a percentage of the load carried by that pick point, by that sling. And here it is illustrated in formulas. For sling 1 loading, we have distance 2 divided by the total distance, this term multiplied by the total loading. For sling 2 loading, we have distance 1 divided by the total distance multiplied by the total loading. I have variable names illustrated over here. The only variables that are really in the formula here are the distances, distance 2, distance 1, then total distance, and the total load. Total load is 26,500. Our total distance is 12. That's the 9 feet plus the 3 feet, or the total distance of 12. Then we have distance 2, which is 3 feet. Once we plug everything in, it's a simple matter of doing the math. 3 divided by 12. Yeah, I know most of you could probably do this in your head, but use the calculator. Especially on certification exams, go ahead and use the calculator. Don't take a chance on fumbling something in your head. But 3 divided by 12, we end up with 0.25. Now we multiply 0.25 times the total load weight, which is 26,500. And we end up with the loading for sling 1, 6,625 pounds. Out of this 26,500 pound load, only 25% is being carried by sling 1 because of the position of the center of gravity relative to the different pick points. Now there's a shortcut method we could use to find the loading on sling 2, but let's go ahead and use the formula and go through it using the formula. Then I'll mention the shortcut after I go through the calculations. We plug everything up. D1, 9 feet. Total distance 12, same as the previous calculation. Total load is the same. The only thing different here is the distance, the D1, 9 feet. 9 divided by 12 is 0.75. Let's go ahead and check it. So we end up with 0.75 multiplied by 26,500. 19,875 is the loading on sling 2 with this rigging configuration, with this position of the center of gravity relative to the position of the pick point. Sling 2 is carrying 75% of the load weight. Now the shortcut that I told you about, let me go ahead and mention that. Once you calculate the loading for sling 1, we know what the total load weight is. So we could take this total load weight, 26,500, and subtract the loading on sling 1, and that would give us the loading on sling 2. If you ever are in a hurry and you need to take the shortcuts. I like doing things step by step, keeping everything straight, in order, especially when I'm showing folks how to do this kind of calculation. I go step by step, iteration by iteration, so I don't lose anyone. But there are shortcuts that can be used periodically if you need to use those shortcuts. All right, well that's an example of how, or that's the method we use when we need to determine sling loading in a situation like this where the center of gravity is not dead center of the load. When we have an odd-shaped load, or when we have a load with an uneven weight distribution. This is how we would find the sling loading. All right, let's talk about something I think is really, from my work in bridge construction and some heavy lifting, I think determining the pick points is really the starting point for a lift where you have maybe 2 different cranes with different capacities, or you have odd-shaped loads, whatever the case may be. Determining those pick points is crucial to help prevent overloading the rigging or overloading the cranes that you're using. And here's a type of situation that a safety professional or a project manager may find themselves in when it comes to lifting a heavy load like a girder assembly. Let me just read through this scenario, and then we'll, over the next several slides, we'll talk about how we determine the pick points. A company needs to lift and place a 265,000 pound girder assembly. It's 150 feet long. The load weight is evenly distributed, and the center of gravity is located at the object's centroid. Again, centroid, just a fancy term for the dead center of the load. It's not an odd shape. It's uniformly distributed. The weight is uniformly distributed. So the center of gravity is at the dead center of the load, which makes it easy. Or that aspect easy, at least. We have two cranes being used to lift the assembly from the ground and place it. So each end is resting on pier caps 60 feet in the air. The load on crane 1, that's going to be this crane over here, this side over here. The load on crane 1 cannot exceed 145,000 pounds. The loading on crane 2 over here cannot exceed 120,000 pounds. Now, what a lot of crews, a lot of companies may be tempted to do is just they place the pick points so that each crane carries an equal load, which in this case, an equal load would be 132,500 pounds. But if they do that with cranes that don't have the same capacity, there's the chance that one of the cranes could be overloaded. That's what would happen in this situation. Again, crane 2 is only good for 120,000 pounds. So if we place the pick point so that each crane carries an equal load, 132.5 is going to exceed the crane 2 limitation. So what lift directors and riggers and other folks that are involved in this process needs to do is to determine the position of pick points so neither crane is going to be overloaded during this lift, during this operation. Crane 1, greater capacity and will carry more of the load. To carry more of the load, the pick point needs to be closer to the center of gravity. That's why I kind of have these slings positioned off center in my diagram. Crane 1, more capacity. They need to carry more load. To carry more load, to put more load on that crane, this is going to be closer to the center of gravity. Crane 2, well, here's a formula. Same formula that we used in the previous problem when we were finding sling loading. We're going to use this formula to find pick points also, but more on that as we move along. Crane 2, lesser capacity, will carry a lighter percentage or a lower share of the load. The pick point needs to be further from the center of gravity, so it's going to be further away from the center of gravity. And here's the formula that we would use to determine the pick point for this also. I want to say a little bit about crane capacity before we move on. Crane capacity is normally going to be either your chart capacity or the line capacity. And if you need more information about that, I've talked about it in other videos. We've talked about it in class. If you need more information about chart capacity, line capacity, let me know, and we'll review that. But it's usually based upon chart capacity or line capacity, and other conditions may require what we call derating the crane or lowering the crane's capacity. If we're working on a barge, if we have a barge out in the middle of Lake Hudson and there's a crane sitting on top of it, the movement of the barge, the list and trim of the barge, that movement requires us to lower the capacity of that crane. If we have less than optimal ground conditions and there's no way to improve those ground conditions, we need to lower the capacity of the crane. Wind conditions, or if we're doing any kind of duty cycle lifting. Duty cycle lifting is when we have high-speed repetitive lifting. When we're hanging girders on a steel erection job, or when we're swinging a concrete bucket over and over and over again at a pretty high rate of speed. Those are duty cycle operations, and those need to be derated, or the crane needs to be derated during those types of operations. What I really want to mention about crane capacity in situations like this, again, we had our crane capacities in this problem, 145,000, 120,000. We had those as our limits that we don't want to exceed. Best practice when doing any kind of heavy lifting or any kind of lifting is don't take the cranes to their limit. 80% of chart capacity, 85% of chart capacity, or it could be line capacity. These are common limits that companies impose upon themselves during their lifting operations. I say companies self-impose these limits. Not all companies do. Some companies will take the cranes to the load limit, to the load capacity limit and beyond. And when you exceed the crane's capacity, you increase the likelihood that you're going to crash your crane, that you're going to have an accident. Now for this problem, I'm working off of real charts. We're not going to go into that in detail, but for this problem, the capacities for each crane are 80% of a chart capacity that I was working off of. I set the limits at 80% of chart capacity. This setting it at 80% of chart capacity, that gives us an additional safety factor when we're making our picks, when we're planning our lifts, when we reduce our capacity, self-impose that reduction on our operations. That just helps ensure a safer operation. Another note on crane capacity, one of my pet peeves. Many companies, and I'm talking about the management of many companies, misunderstand crane capacity. As a result, crews end up with undersized cranes on their jobs. The cranes are undersized. They end up having to take those cranes to the max or beyond the max. From a practical standpoint, a 150-ton crane, 150-ton rated crane really cannot safely lift 300,000 pounds. Just in very limited situations will that 150-ton crane be able to lift 300,000 pounds. A lot of our management, they don't get it. They'll send a crew out with the crew needs to set 100,000 pound girders, so they send them out with an 80-ton capacity crane thinking, well, 80 tons, that's 160,000 pounds. They've got plenty of capacity. But the longer that boom gets and the longer the radius gets, the more capacity they lose out of that 80-ton capacity crane. And an 80-ton capacity crane, generally speaking, is not ever going to be adequate on most bridge jobs for hanging 100,000 pound girders. But back to our problem, and since I went on that rant, that was longer than it should have been, let me go back through the problem. Again, we have a 265,000 pound girder assembly, 150 feet long, and we're wanting to set it each end on pier cap 60 feet in the air. The real kicker here is that one of our cranes, we're using two cranes, one of them can't lift more than 145,000 pounds. That's a self-imposed capacity limit that the company's placed on itself. Crane 2 cannot exceed 120,000 pounds. We need to place our pick points so that we don't exceed either of these limitations. The first step in this process is to determine our desired distance between our pick points. Again, we have two cranes, two pick points. What distance do we want between those pick points? And it really doesn't matter. What I like to do, we could use 75, 85, 100 feet. What I like to do most of the time is go with 1/2 the load length. We have a 150 foot long girder assembly, so let's go with 1/2 the load length for our distance between the two pick points. 150 divided by 2, we're going to have 75 feet between the pick points. But again, that could have been 85 feet, it could have been 100 feet. It's whatever we need for that particular lift. And there are numerous variables that may affect the distance you need between your pick points. But if you don't have extraneous variables affecting that decision, I go with 1/2 the load length. In this case, it would be 75 feet. And that 75 feet between the pick points, between our slings. Again, here's our pick points. Then I got slings to further illustrate those pick points. That 75 feet distance between the two could be here, it could be here, or it could be back over here. That center of gravity, all we know for sure right now is that the center of gravity is going to be between our pick points, within that 75 foot area, within that 75 foot distance, or it's going to be somewhere in there. But we need to find exactly where each of those pick points should be located so that we're not overloading the crane. Again, this is the first step. select the desired distance between the pick points. Now we can move on to determining the exact location for these pick points. This is another diagram of what we're working with. We have the 150-foot girder. We have 75 feet between our pick points. We have 265,000-pound load with a center of gravity dead center of the load. What we need to find is distance 1 and distance 2. What are the distances between the center of gravity and the pick points? And to do this, we can use these formulas. We can use this formula to find distance 2, and we can use this formula to find distance 1. And what we're going to do is plug all of our information in that we have and then solve for distance 1 or distance 2. Go ahead and walk through that process. For Sling 1, 145,000 pounds is our max. So we're going to set that as our sling loading for Sling 1. As our loading for Sling 1. Our distance between pick points, our total distance is 75 feet. Go ahead and plug that in. Our total load weight, 265,000 pounds. So now we do a little bit of algebraic transposition to solve for D2, and we're going to find what our distance is for D2. Again, sling loading 1, we're finding D2. We multiply both sides times 75. It cancels on the right side of the equal sign, and we end up with 145,000 times 75 on the left side of the equal sign. And we're trying to get D2 isolated on one side of the equal sign. Everything else on one side, the unknown variable D sub 2 on one side by itself. The next iteration is to divide both sides by 265,000 pounds. When we divide both sides by 265,000, it cancels on the right, and on the left we end up with 145,000 multiplied by 75 divided by 265,000. Let's go ahead and I've got the 10,875,000 in there. Let me go ahead and check the math. We have 145 multiplied by the 75, and 10,875,000 is correct. Now let's divide that by the 265,000. $41.037. I'm going to round that to 41.04. That is our distance for D2. D2 distance is 41.04 feet. For Sling 2, or the distance 1, we're going to use the same formula, same process. There is a shortcut that I'll show you here in a second, but let's go ahead and go through it step by step, plug everything in. Sling loading, Sling 2 capacity is limited to 120,000 pounds, or Crane 2 capacity is limited to 120,000 pounds. So we plug in 120,000 for our sling loading there. Total distance is the same, total load is the same, and we're solving for D sub 1 or distance 1. And same process. Multiply both sides by 75, cancels on the right, we end up with this on the left. Then we divide both sides by 265,000, cancels on the right, we end up with this on the left. Now we do our math. And I know some of you are just chomping at the bit about, you've recognized what the shortcut would be already. But hold on, we'll talk about that in a second. Like I say, I like to go through all the steps, step by step, so nobody gets lost. 120,000 multiplied by 75. Looks like 9 million divided by 265,000. 33.96. 33.96 is our distance for D1. when we add 33.96 to 41.04, we come up with 75 feet for that total distance. The shortcut I mentioned, which most of you are probably already anticipating, once you find D2, you can simply subtract it from 75 to find D1. Once we have D2 over here at 41.04, 75 minus 41.04 is 33.96 feet. So feel free to use that shortcut if you need to. But like I've said many times, I like to go through everything so I don't lose anybody. One more thing I want to do with this, I want to proof this. And what I'm talking about with proof is we're not talking about geometry and the proofs that we write in geometry. I want to go back with these numbers that we've calculated, plug them back into the formula to see if, sure enough, we come up with the sling loadings that we started with. We started with 145,000 as our sling load, and we determined that the distance for distance 2 needs to be 41.04 feet. Plug all this back in to calculate sling loading, comes out 145,008 pounds. A little difference. That difference is due to rounding. I've rounded everything to 2 decimal places in the previous problem, the previous solution, and when we use those numbers, we're going to be a little off, but we're still within our safety factor for this particular operation. Same thing for sling 2. We plug our distances in that we calculated, and we come up with the sling loading that we would expect to see. All right, one more thing I want to do, because I'm sure there are probably some skeptical folks out there. I want to show you how this distance, this total distance, doesn't really affect what we're doing here. If we wanted to go with 85 feet instead of 75 feet, that would have been fine. So let's go ahead and work through the problem again, but we have 85 feet as our total distance. Using the same formulas, plug in 145,000 for sling loading, 85 for our total distance, 265 K is the weight, same as before. We're solving for D2, same steps that we went through before. We come up with a different distance for D2 when we have 85 feet as our total distance. Same thing with solving for D1. We come up with a different distance for D1. 38.49 feet, 46.51 feet. Add these together, they add up to 85 feet. But let's proof this one also. When we take those distances that we calculated and plug them back in, we come up with 145,008, 119,992 pounds. Within that range where they need to be if this is an accurate procedure. So 75 feet works, 85 feet. You may run into situations where you need 100 feet between your pick points, or maybe you only need 60 feet between your pick points. There can be obstacles, obstructions in the area that make it difficult to sit cranes in certain areas, which affects your pick points also. There's one more issue I need to mention with regard to this concept that we've been working with. I need to talk about pick point versus hook point. If we have a multiple crane pick and one or more of the cranes is swinging multiple leg slings like we have here, we're not going to measure from the pick points. Again, the pick point is the point on the load where the rigging connects to the load. In this rigging design, we have 4 pick points. In this type of configuration, we're not using these pick points to determine the load share. We're using the hook point. And this is our hook point right here. We have our hook and the hook point for each of these rigging configurations, for each of these sling configurations. Again, use the hook point in these types of scenarios. And the hook point's going to be, when you're planning your lift, you're getting ready to make your pick, the engineer or the lift director, they're going to mark the location on the girder where that hook needs to line up with. They're going to put that mark on the girder. The hook needs to be directly above that mark. If they're one way or the other, it's going to affect the loading on the cranes and the loading on the rigging. And that's another thing about, we're talking about loading on the cranes in this particular problem. But these types of problems also need to, these types of calculations need to also be executed to help us ensure that we're not overloading the rigging that we're using, because that's also a concern. All right, let's go ahead and summarize. If you have any questions, I know I kind of sped up through that last slide. If you have any questions, let me know. Email, text, call. You have that information available if you're an NSU student. But just to summarize, the center of gravity affects sling loading. For multiple crane picks, we need to know the load center of gravity and the distance from the center of gravity to each hook point. Now, let me go back to this hook point one more time, one more slide. The reason this is important, the problem that I showed you to illustrate this process, that is really simple, where you have one pick point for each crane. In reality, it's usually not going to be that simple. You're going to end up with rigging designs more like what we have here, where you're going to have more concern about the hook point and how it affects loading than the pick point and how it affects loading. So this is really a more realistic scenario, especially if you're doing a 265,000 pound pick. This is going to be more realistic. It's usually not going to be just a single vertical leg sling for each pick point. I mean, it could be. You could also end up with one of your cranes has a rigging design like this, and one of your cranes would just have a single vertical also. All right, back to my summary. Like I said before, just to reiterate, what we're doing here also applies to our rigging selection to make sure that we're not overloading our rigging. A multiple leg sling may have different loading on each leg. We need to calculate the loading and choose rigging accordingly. Center of gravity and load share needs to be considered when determining hook points during lift planning. And a lot of companies, I say a lot, some companies overlook this. I would guess most companies that are doing this kind of heavy lifting, they are dotting their I's and crossing their T's, doing it correctly, making sure everything's checked and double checked and rechecked before they're putting 265,000 pounds up in the air. But there are also some companies out there that may try to play fast and loose with the planning side of it, and they don't give proper consideration to hook points and center of gravity and load share and those important variables that we need to pay attention to.